Hello. So the purpose of this short video is to introduce and also summarize lecture 28 of Introduction to Data Structures that concerns hashing. So what is the problem? Our problem is to map data into a table. So we have some data objects. I want to store them. So storing them into a table, you can think of a table as a sequence of some storage elements that we have available. So we're going to do this by assigning to every data element, or we will assign to every object an index. So the elements in the table are indexed and we have objects. And how are we going to do this? We're going to apply a hash function h that goes of the space of all objects, assigns to every object a key, and with every key belongs an index. So our objects can be anything, but typically objects have a string representation. As we know, a string is a sequence of bits, is actually a number. So the string representation is one way to assign to every object a key. So that is typically application dependent. So we have here our h function. Then if we have a number, we have to map it into this index space. And the way that we do that is actually canonical. So that's taking mod n. So if you have 5 elements, we do modulo 5 for every number that we get here. Now what is the problem? What is the problem is that we may have objects that map to different keys, but we may have different keys that map actually to the same index. So that is the collision problem. And that's actually the problem that we will address today. So we have 2 different keys, but we have the same index. Implying that they will end up at the same position at the table. Let's look at an example. So we're going to map some keys, say 42, 43 to 52. In a table with capacity 5. So we have a table of capacity 5. So we can represent this as follows. These are the keys. So to place these keys into the table, we do modulo 5. So the division after dividing by 5 of 42 is 2. So we place 42 at index 2. Likewise, 43, remainder after division by 5 is 3. So we paste it in 43. No problem here. Now the first problem arises with the number 2, which actually we would like to place at the same spot as 42. Now we have a collision. So one way to resolve this is to apply open addressing. With open addressing, we're going to look for the first open spot where we're going to place 2. We cannot place it in 3 because that's occupied by 43, so we place it in spot 2. So we place the next element in the next open spot. So 2 modulo 5 was 2, but we could not place it at position 2 and 3, so we place it in position 4. Now what happens when 52 comes in? 52 doesn't fit here, doesn't fit there, doesn't fit here as well. We cannot go over the index, but when we assign, we do +1 modulo 5. So 52 lands over here. That's one solution. The other solution is not to work with a table of numbers, but with a table of nodes that contain numbers. So that's the chaining approach. So in chaining, we have actually again a table of 5 entries, but now we have pointers to nodes. So when we deal with 42, we're going to create a new node, 42. When 43 comes in, we have a link, a pointer to the node 43. When 2 comes in, you already see it coming, we can just append to this list. So the spot 2 is actually occupied by 42, but there is space enough for just another node. And the same we can do with 52. So with chaining, we use a linked list of nodes. So these are 2 solutions to this collision problem. The open addressing works with tables of fixed capacity. If you have somehow an idea on the total number of keys that you want to store, then that is recommendable. With chaining, you have an unlimited capacity. So if you don't really have a good idea how many keys you are going to map into your table, then you can use chaining. Both approaches have the disadvantage, however, that when there are many collisions, it will slow down the lookup in this table. So that is a very brief introduction and also summary to the topic of lecture 28. As always, please consider the slides that are posted and also the code. That's it.